time for us to talk about heat, and specifically the flow of heat, because you can't stop it. Heat is a property of matter derived from the movement of its atoms or molecules. And we can slow it down with insulating materials, but we can't stop it. So we talk about the flow of heat. And we'll do that with this classic experiment of mixing two measures of water together and trying to figure out what the resulting temperature is. Now, as long as these materials are the same and the quantities are the same, your intuition will tell you that when we mix them together, we'll just get a simple average of the two materials. And that's perfectly true. But we've got to go beyond that. And to do this, we use this equation. Q is the flow of heat, M is mass, C is the heat capacity of the particular material, and delta T is the change in temperature. Now again, I'm introducing a Greek letter here. Delta, this triangular figure, means change. And we'll go into exactly what change means. But first, let's look at what we've got to work with. Here's a bucket of water, and it has an initial temperature that I'll call T super I. The I stands for the initial temperature. And we'll give it a subscript of A, because it's sample A. Similarly, we have sample B, and an initial temperature for that sample. Tagging along with these things is the mass and the heat capacity for each of these materials. But we're not going to bother with that in this first example. So I'm going to take that right out of the equation to simplify this concept in our introduction. We've got identical masses, and we've got identical materials. So the only part of this equation that's going to matter is the change in temperature. A key principle of this type of analysis is that we say when we mix these two samples together, the change in the heat of A is going to equal the change in the heat of B. And that's intuitive when, again, we have similar materials and similar samples. But to the degree that A loses temperature, we'll say that B gains just that amount of temperature. And that's not intuitive. But that's how these analysis work. So let's look at the change in temperature, delta T. We'll start off with an initial temperature for the sample A. Delta T in this case will be T initial minus T final. And by T final, I mean what comes out of the mix. It starts at one temperature, mixes with another sample, and comes out to a different temperature. We'll call sample A the hot one, and that's why I've colored it red. In that case, we know that the initial temperature will be hotter than the final temperature. And we try to keep all of our delta T's positive so that the algebra works. In the opposite direction, sample B is cooler, and so we'll reverse delta T. We'll say that the final temperature is warmer, than the initial temperature. So the warmer temperature minus the cooler temperature will again give us a positive result. And in fact, since we've simplified this equation with the same mass and the same heat capacity, this equivalence from the flow of heat of A and flow of heat from B carries through to the change in temperature. Now, let's do a little algebra to work this out. If we keep the initial temperature of A here, and we add the initial temperature of B to both sides, this cancels out, and we get the initial temperature of B over here. Similarly, if we take the final temperature of the mix and add it to both sides, this cancels out, and we get two of them over here, because the final temperature in both equations is going to be the same. We've only got one bucket, it's only going to be one temperature, so we only get one final temperature. Simplifying, we divide both sides by 2, and we get the final temperature is going to equal the initial temperature of A times the initial temperature of B divided by 2. It's just that simple. It's an average. Now this is going to get more complicated as we change the mass and we change the heat capacity. But that's the introduction I want to give you today of how this formula for the flow of heat works. Let's look at an example. If the initial temperature of A is 80 degrees and the initial temperature of B is 20 degrees, let's substitute into this formula and see what happens. We're going to get a final temperature that equals the initial temperature of A plus the initial temperature of B divided by 2. In this case, it'll be 100 divided by 2, or 50. Now, we want to check this to verify that we're on the right track. So again, let's look at, is the change in temperature of sample A equal to the change in temperature of sample B? Well, here's what delta T looks like on both sides. The initial temperature of A was 80. The final temperature was 50. For sample B, the final temperature was also 50. The initial temperature was 20. If we do the arithmetic, we see a similar result for both delta T's of 30 degrees. Again, always the change is always positive. So this verifies the fact that this equation works, at least in the case where we're using the same materials in the same amounts of materials.